Okay, let's talk about trusses. Trusses are efficient and economical to span a long distance. Okay, so it has to be, what is our perception of a long distance? It depends on the type of work that you and your office are doing to define that. So I'll show you a chart that talks about economical design, sort of the ranges for trusses, but where you get the most economy out of them, and a few charts coming up. But also when we talk about spanning a long distance, for some of us, if we're doing residential design, 20 feet or more may be a long distance, but for others of us, if we're doing stadiums, the span may be 700 feet, okay, the Seahawks Stadium out in Seattle. So we'll put into perspective into these charts what is economical and when do trusses become the most efficient use instead of a rolled section or another member. Trusses are an efficient system of members stressed primarily in axial tension and compression. Okay, we want to talk about that. The key word here is primarily. Okay, when we look at the method of joints and sections, we're going to see that we're going to determine, is the member in tension or is it in compression? But when we talk about primarily, what we're talking about is there may be bending within the member as well. And if we have a simple triangle, okay, and we put a point load on top of this member, and this is member A, B, and C, and we can show another similar triangle next to this. A point load on the top and also a point load hanging off of the bottom chord in this situation. And again, we have member A, B, and C. What is member C stressed in both of these locations? Well, in truss number 1, and we can call this truss number 2 on the right, if we push down on this with a point load, the load's going to go through members A and B. These members will be in compression as they resist that load and are acted upon by the support. And member C prevents these members from spreading out, and it's in tension. So it's a tension member at the bottom. So it's primarily stressed in axial tension. But if we start to look at truss number 2, again, members A and B will be in compression. They're being compressed by the load on the top. And also member C has to be in tension to prevent those from spreading out. But now, since there's a point load hanging off of member C, it also has a combined bending associated with it. So we have to be able to identify those items where there's a combined bending, okay? Trusses do not like bending within their chords and members, so we want to load the truss at the panel point. So watch out for items when you start to see loads that are not at a panel point. There may be some additional bending in that member besides the axial tension and compression load. When you start to get into larger members, such as some of these stadiums or longer span trusses with heavy members, these members have a self-weight to them as well that has to span in between here. And in these bigger members, or these bigger trusses, we better not overlook the self-weight of the top and bottom chords that stand as beams between these members, okay? On lighter, typical trusses, the self-weight probably won't control the design and have much effect to it, but we still need to consider it. So it's one of those things, look for obvious point loads beyond just the self-weight of the member that's inducing the bending into it. Okay, so loads are applied to trusses at their panel points. If the loads are applied at locations other than the panel points, and we'll get into the panel points and on the next page coming up, talking about this concentric loads, a bending moment is induced into the connections or into the members. Okay, this is bad. Okay, so if you're to think about when we think about trusses, just primarily we want to load things at their panel points and avoid the bending. So it's the bending what I'm saying is bad in this scenario. Understanding which portions of the truss carry which forces. Okay, we talked about our shear diagrams, we talked about our moment diagrams and various definitions. Now it's time to work with materials and systems throughout the rest of the class. The webs of the truss carry the shear. So these internal diagonal and vertical members are what carry the shear forces. And the bending members, or the bending, is carried by the chords. So the top chord and the bottom chord resist the bending. So that's where we start to get the understanding. And if you look at the active statics program, if we have a truss, where is it going to be critically sized for the chords? Well, it's going to be probably at the midspan where the bending would be the greatest. And where would the webs be the greatest in size? Probably near the ends, near the supports, they're going to be the biggest. Okay, so when we talk about economy of design, let's draw up here a larger scale truss. When we economize the design, we still want it to be bolted together pretty easily. Let's see how many panels. Okay. So if we have our truss member, and let's say this is spanning 180 feet, okay, with these panels. And looking at this, we know that we can't ship this all in one piece, okay? So it's going to need to be erected at the job site and fabricated and put together and set on top of the columns. Okay, so when we look at this, how do we economize the truss? Well, the trusses get their efficiency in terms of their use of material. Okay, so if we're going to splice the truss, maybe we're going to put a splice point in here and here. Okay, so we can start to look at, if we're going to splice this member, we have an opportunity now to use different members for the top chords where the stresses and also the bottom chords, how they change, understanding the moment diagram. If we were to think about a moment diagram, it's greatest in the middle, and there's less moment and less stress near the ends. So maybe for this middle piece, I'm going to use a heavy W14 member. So we can write in here, maybe it's a W14 by 211 like we had for that column. And we can use that at the top and the bottom, even though they'd probably be different. But just to make a point, now, if the rest of the truss doesn't need to be that heavy for the top and bottom chords, we want to cut down the amount of material. We don't want it to weigh 211 pounds per foot. But we want it to be in the same family as the W14, so it splices together nicely. So we would use a lighter W14 in these zones. So maybe a W14 by 170 something, or I'm just making that one up. Okay, so we've dropped the weight and we're using lighter members. But remember about the detailing. Okay, they still have to be bolted together at the splice and be similar in that instance. And the same thing with the angles. If we think about a shear diagram, it looks like this. The shear is greatest near the supports, and it gets less in the middle. So we would expect our angles and web members on the ends to be the greatest. So maybe I want to do all the diagonal web members with double angle 6 by 6. So why shouldn't I just use double angle 6 by 6s for everything? Maybe these are a 1/2 inch thick. Okay, and then when we get to the next set of angles to economize this, maybe these angles are double angle 6 by 6 by 3/8. Okay, so just showing you we've kept the detailing the same. Everything's a double angle 6 by 6 and it all bolts up the same at the gusset plates because of the geometry, but I'm reducing the material in the weight based on the thickness. So that's another way. This is how you get economy out of the truss, putting the material where you need it, okay, and thinking about the detailing as well. So we don't want to just change every individual member to be different for the sake of changing it. Okay, look for a rhythm within the design. Okay, let's talk about work points and those systems of concurrent forces. Okay, when we talk about a work point or a system of concurrent forces, it's all the lines of actions of the centroid go through one common point. And we start to look at things that are detailed appropriately, that not only feel good architecturally when you look at it, but it's right structurally, is being able to look at these center lines of these members and being able to draw the centroid through these. And they all coincide at a common work point. Okay, so as the load is injected into this system as it pulls down, it injects tension and or compression. In this case, it's tension into these threaded rods directly into the system. Okay, so that's our system of concurrent forces. And again, this shows the importance of the centroid. That is what we are lining up on all these members. If your centroids do not align, then you end up with a bending moment. Okay, let's imagine if this threaded rod ended up connecting right here on this member. Okay, so as it came down and was connected, if this load pulled down and this was pulling up in resistance, now we have two equal and opposite forces separated by a distance, and it starts to bend this member and we get bending in the connection. So concurrent forces eliminate the bending. Okay, what I'm talking about right now with concurrent forces, and we can also call this concentrically loaded. This is against what we talked about when we talked about the eccentrically braced frame. When we talked about the eccentrically braced frame, we wanted the bending moment in this system to dissipate energy. Okay, we wanted these braces to be spread out, and that's what gave us the yielding mechanism. Typically, you want concentrically loaded systems, but in terms of a seismic system, an eccentrically braced frame is a good system to dissipate energy through bending. So that's where our conversations are a little bit different with these. And even in three-dimensional systems, we can start to see the work points and how these braces that support this terminal all come together. Okay, so that's what we mean by a system of concurrent forces, and this would be the work point right at the middle. You may see that on your shop drawings, or you or the engineer may call it out on the design drawings as well. Panel point or work point, typically the same nomenclature. Okay, let's talk about various truss systems and the ones to get to know for the exam. Okay, I would say most of us are probably familiar with what a bowstring truss looks like in terms of seeing that and utilizing that in practice. I think we can all pick out what a scissors truss looks like, okay, as it vaults on the inside and outside. Okay, but the ones that we want to focus on are these names of different parallel cord truss members. And we'll start with the Howe truss, the Pratt truss, and the Warren truss. Okay, being able to identify the differences between these when they're used and what their benefits and disadvantages are. So how can we identify? The first thing to know is the Howe truss and the Pratt truss are pretty much opposite from each other in terms of definition. Okay, the Howe truss says the diagonals are in compression and the verticals are in tension, versus the Pratt truss, the diagonals are in tension and the verticals are in compression. So these two are the opposite of each other. So we need to be able to identify these. And these are talking about when you're pushing down, this is assuming the load is going down into these systems, okay, of how they behave, that the Pratt truss diagonals are in tension, the Howe trusses are in compression. And then we also have the Warren truss. And I would say the Howe truss and the Pratt truss, these are good for floor systems, okay? Versus the Warren truss, this is good for a roof system, primarily, because it talks about stress reversal. It has diagonals going both directions that may be subjected to tension or compression. And shortly we'll be talking about what if there's a wind uplift on this roof, and we've talked about wind. Sometimes the load is pushing down, sometimes it's pulling up on this truss, so those diagonals have to be able to function both directions, okay? Versus a Pratt truss, if these are slender diagonals, such as what we saw in this footbridge, okay, I can just keep it on the blow-up picture, I guess. With the footbridge, we have these slender diagonals, and if it was ever subjected to an uplift force, these members would go into compression, and threaded rods are not very good in compression. So this is a Pratt truss, actually, in this footbridge that we're looking at. Okay, so understanding that those rods will buckle, and they would be useless in a compression load the way that they're economized. So how can we remember the names of these? You need to definitely know these definitions to identify these, okay? But what's a way to identify them on the exam and in practice when you're starting to do those things? Well, here are some different ways to look at them, okay? One of the ways that I used to talk about with the Warren truss, there's a W at the end and there's a W at the beginning of Warren, okay? So we start to see the alternating diagonals and this condition, okay? And also with the Howe truss, somebody pointed out in class one time that there's a W in the middle of Howe and there's a W in the middle of this truss. Okay, so your Howe truss and your Warren truss both have the W's. So the last one must be a Pratt truss, but there's really not a way to draw a P or a T or anything in there with that. So I would say it's your Warren truss and your Howe truss that you can have a little rule for yourself of how to identify it, okay? What is the truss if we take away all of the diagonals? Well, it becomes a Varendale. Okay, so that's a specific name for a truss that doesn't have a diagonal. And what it really has, it has moment connections at the ends. Okay, and it becomes very expensive It's no longer a pin condition. And it says down here its advantages and disadvantages is it allows unimpeded movement through the bays, may be used for the entire building frame. It's inefficient and expensive since all the members are subjected to bending. Okay? So what if we go back to our truss on this page that's 180 feet long? I can put up the polling questions here. How deep would this truss be approximately? And I'll put some choices up here. Okay, so you should have seen A, B, C, and D pop up. So approximately how deep would this truss be? And A, maybe it's 8 feet deep. B, 12 feet deep. C, about 18 feet deep. And D, let's say 24 feet deep. So what's the best answer? A, B, C, or D on the approximate depth of this truss? All right, so the answer that I would go with, and I'll give you this rule of thumb on the exam, and Sid's got the answer that the deepest one probably works, but may not be the most economical. I would go with 18 feet on this, okay? And I'll show you where we can get some of these rules of thumb, that the span to depth ratio would be about L over 10. So if we know the span is 180 feet deep, just divide it by 10, and it's approximately 18 feet deep. You could maybe get down to 16. You may go up to 20 depending on the loads and what you do. I would say 12 would be pushing it. Once you're in the 10 to 12 foot range, you're spanning about 100 feet or 120. So to go another 60 feet, you may have to post tension or pre-stress the truss if you have that, and some of you may have done that on your job. And that's where with the span to depth ratios, that's why I think the Architect Studio Companion and some of these other articles like this one here give you the best guidelines so that you're not skewed by this, because somebody may say, Mark, I just spanned 180 feet with a 12-foot truss, and depending on where you are, you may have done that, okay, depending on how they reinforced it and so on. But let's look at these span to depth ratios, and you'll find these in the Architect Studio Companion as well as other general structurals books. So you went L over 8 to L over 12. So if we did L over 12, 180 divided by 12, still puts you at 15 feet, right? So 12 feet would still be too short. Okay, so what that means is, let's talk about that. It means it's the length divided by 12. Okay, so if we had 180 feet, and if you divide that by 12, it means it'd be approximately 15 feet deep. Okay, and if we did it with 8, it would be even deeper than that. So I would say the rule of thumb, since these are all over the place, is to go with L over 10, because L over 10 is between L over 8 and L over 12. For your Pratt truss, it's L over 10 to L over 15, so it encompasses L over 10. The same with the Warren truss, L over 10. And your Varendale is back to L over 8 to L over 12. So I would say within that range, L over 10 would work for all of them as just a rule of thumb to get in the ballpark. Do you understand what I mean with this L over 12, why it would be 15 feet deep then? Okay, great. So that's why I would say just getting these together, and definitely I appreciate you looking at the chart and doing that, because that's great and what we're here to talk about. And so I would say if I could just pick one to keep in the back of my mind and to keep as a rule of thumb for trusses, it'd be L over 10, and that should get you in the preliminary design ballpark. Okay, so be familiar with just the various truss names. Again, now we see the how in the Pratt truss. But now, with the pitched top chord, or the non-parallel truss chord, do you see that the diagonals have changed directions versus the parallel chords? If you compare the Pratt and the Howe, the diagonals have now reversed. So it's not the direction of the diagonals that you have to memorize, okay? It is the definition. The definition says that for a Howe truss, the diagonals are always in compression. So when it's a parallel chord truss, this is the direction of the diagonals to keep them in compression. When it's a tapered top chord, this is the direction of the diagonals. So the diagonals are always in compression, the verticals are in tension, and it's just the opposite for the Pratt truss. Okay, so these are various trusses to get to know, if you don't know those, just to be able to identify various systems and their advantages and disadvantages. How can you tell in the Howe that the diagonals are in compression? Well, I'm going to prove it to you with the Pratt truss, and that's where it's going to take some, that's the geometry that tells you that, okay, that we're looking at. Okay, that's how they would be configured. But now we're going to go through an exercise with a Pratt truss with loads on it to show you that they're in tension, the diagonals, and the verticals are in compression. It would be just the opposite for a Howe truss. So we're going to work through that. So that's a great question, right? Because it's like, yeah, we believe you, but how can I prove it to myself? And so now we're going to prove it with some numbers, that those geometries will hold true if the loads are uniform and downward on it. Okay, so how do we apply loads to a truss? And this is the Pratt truss in our example that we'll work with shortly. And why I picked this example or these pictures, this is actually at in Monterey, California, at the aquarium at the footbridge within there. Okay, and this really shows applying loads at the panel points and applying loads away from the panel points. I would say maybe L over 7 for that. So Brian asks if there's an average. Yeah, L over 6, L over 7, because I see there's a 7 there, a 7 in here. So L over 6 to L over 7 on that. I think that's a little bit more obscure than the L over 10. But yeah, if you can write a rule for yourself, that's about where you would be. Okay, so this footbridge, if we look at it, and it has all the various components of the load path, think about these beams support the floors and the people walking on this system. And they get their load to the system by spanning this way. So why are there beams in between the panel points? Why can't we just load it at the panel point or at this vertical? This is where we want the loads to come in, to be injected into the truss. So why the extra beam? Well, I bet it has to do with this wood flooring. It can probably only span 6 feet. It can't span 12 feet. So if you have a 100-pound per square foot live load on this system, and there are people walking up here, then there needs to be an intermediate beam so that the wood will work out. But the truss only needs its bays at about every 12 feet on center. So they've put in an intermediate beam. So this is a great indication of every other beam loads the truss directly at the panel point, and it injects the load into the system. But at the intermediate beams, it induces the combined bending. Okay, it's a point load in the middle of the beam. So it wants to bend downward. What's the bending moment on this beam? Well, we could probably simplify it. It's just a point load in the middle. And the span, we could find that very quickly, right? M max from our loading diagrams equals PL over 4. Okay, now that you'd have to calc it, but that would be the approach. That this is just a simply supported beam. It has continuity, but we could simplify it in practice and just put a point load on it. as a simply supported beam and then design that as the maximum moment. Okay. Also underneath this system, okay, we have two trusses that we have to get the load to and spanning out to the ends. Do you see the diagonals underneath within these systems? Let's see, it goes about every 2 beams. That's our horizontal diaphragm. Okay, if there's an earthquake load or an internal wind pressure pushing on this, that's how we get the horizontal loads back and keep this truss from racking. You can also see it up above. Okay, so these trusses are braced at the top and the bottom with a horizontal diaphragm. Okay, so that's what I wanted to show you with these pictures, the point loads on the panel points and away from the panel points and what they induce into the system. Okay, so let's talk about the method of joints and then the method of section. So our problems here will be we'll work several joints of this to go through this scenario. And we'll do several examples with the method of joints. We'll probably just do one with the method of sections. I would say going into the exam, the method of joints is going to help you out the most. Okay. Right, since the cross bracing is rods, they will always be in tension. That's exactly right. Okay, so that's why they've got them going both directions. In one instance, when you push on this, okay, only one of the rods goes into tension when it pushes through and pulls on these guys. But if the seismic force is coming the other way or the vibration due to the people, then the other ones engage and go into tension. So that's why they're crossed, so that all their bases are covered with, to make sure that they're tension only members. That's exactly right. Okay, so here are rules for the method of joints, and I would say this is, if I was to choose one to go into the exam with, this would be it, and for practice, because the method of sections, when we actually do a truss in practice, okay, we always start with the method of joints. And then if there is, and here's where we'll get to the part where we talked about a week ago, an indeterminate system, if we do not have enough equations for the number of unknowns, and I'll show you an example of that where we'll circle back around in a second. And if it still holds true and we can't solve one of the joints using this method, we'll use the method of sections to solve for the unknown and then continue with the method of joints. So the method of joints is the number one thing to use, okay? On the exam, the method of sections is just going to be a time saver. Okay, I think it's highly unlikely that you're going to have an indeterminate truss where you absolutely have to use the method of sections. Okay, and so I'll show you how we'll use it to save time. Okay, but I would say this is going to be the most rewarding for you, probably, the method of joints for multiple problems. Okay, so let's talk about the rules. And with this, it's solve for the reactions and supports. And you can see we've been doing that the past couple of days. That's where we started yesterday. Be sure to solve for both the vertical and horizontal reactions. Starting at either support or the end of the truss if it cantilevers, systematically draw free body diagrams of each joint to include the imposed loads, any forces on the members that frame into the joint that are known, and the support reactions, okay, if the joint is at a support. And here are rules that we talked about when we looked at that canopy problem. Only X and Y forces are solved for. That is, all the joints are assumed to be pinned and cannot resist bending moments. Okay, so our equilibrium equations are just sum of the X's equal to 0, sum of the Y's equal to 0. Horizontal members can only resist horizontal forces. Vertical members can only resist vertical forces. And diagonal members have a horizontal and vertical component. Now I'm going to show you on one of these joints, and one of the places I used to mess up when I first learned how to do this, okay, again, these things take practice. Whenever I would find a diagonal force, I would try to do something with it at the other end. And we can see in our equilibrium equations, there's nothing called sum of the diagonals equal to 0. Whenever we have a diagonal, we want to get it into its horizontal and vertical components. Okay, so I'll give you also another time saver for the exam about you don't have to find the real forces in all the diagonals, just the one that they're asking for. Other than that, we just need the horizontal and vertical components. Okay, and it'll also potentially save you some confusion with all the numbers that you may have on your paper. Okay, so only X's and Y's. All right, so let's look at our truss. And again, this is one of those problems where before you jump into the numbers, see if we can solve the problem by intuition and understanding how it behaves. So the first thing it says, use the method of joints. What if it said use the method of sections or use the Maxwell diagram? Well, the first thing is don't let anybody tell you what to do, even though we are going to use the method of joints. Okay? If on the exam they say use the graphical method to solve this or use the method of sections, use whatever method you feel comfortable with. Okay? So if you have a process that works for you and it's founded on engineering principles, use that method. Okay? And so don't let these questions lead you down a path that takes too long. And then the next thing is find the forces in AM, BC, and FQ. Okay? So let's look at this truss. It's symmetrically loaded with 6 kip point loads on it. Okay? And with this, when it's symmetrically loaded in this pattern, if we just ignore the ends of the truss for a second because we can see the diagonals flip, this looks like a Pratt truss. It looks like the diagonals should be in tension. Okay? And we'll prove that to ourselves, but if you go back to the picture of the Pratt truss, you're going to see that this looks pretty similar to a Pratt truss, except that the ends of the members change. Okay? They'll probably be in compression, but let's act like we don't know that yet. Okay? So before we jump in, let's see if we can eliminate any of the wrong answers. So what about AM? Well, I'm not sure if AM is in compression or tension. Let's just say we're not that comfortable with it. So we can't really make a decision on member AM at this point. Well, what about BC? Well, BC is the bottom chord of this truss. And if we think about, if we do not have a cantilever member and all the loads are down, whether they're on the top or the bottom's in tension and the top's in compression. So BC, I'm pretty confident, is going to be a tension member. So answer B cannot be correct with that assumption because BC is in compression, and the same with answer D. Okay? And now this tells us that member AM is in compression. It's either 27 or 38. And member FQ, which is out here in the middle, it's either 0 or 6. Okay? So really, once we get to this point, if we can identify FQ as a 0 force member, then without doing anything, the answer has to be A. Okay? So we're going to work through this through several joints, you know, probably 3, 4, or 5 of them, as probably 4 of them. Okay, so, and then the answer's in here, but let's prove this to ourselves. So we'll work through like 4 joints, and then we'll talk about FQ and 0 force members. Okay, so this is one of those things. Don't turn a problem into a mathematical half-hour problem if you don't need to. It's sort of like live load reduction. If you know the rules, then you can intuitively see the answer. Okay, so where we want to start with this is, let's start here at support A and systematically draw free body diagrams to solve the forces in several joints. Okay, so what do we know about joint A? It's a pin support. There's a 27 kip reaction given. And we know that there's a horizontal member and a diagonal member tying into this. Okay, and this is joint A. Okay, so using our equations of equilibrium, some of the horizontals equal to 0, some of the verticals equal to 0. If we have 27 kips going up, we need 27 kips going down. And based on our rules, the horizontal member cannot resist any vertical forces. So the diagonal member has to resist that entire 27 kip load. Okay, so the entire 27 kips goes into the diagonal member. Once you know one component of the diagonal, you get the other one for free. Okay, this truss is 10 vertical by 10 horizontal. It's a one-to-one relationship at all of these joints. Okay, in this class I don't get too much into sine, cosine, and tangent. We're just going to use similar triangles and keep it simple just to show you this. At the end last year when I did a recording and recorded this, I can either put you guys into it. I worked a couple problems with sine, cosine, and tangent, or if we decide to add another class, which I'm up for it, depending on where we are on Tuesday, to look at the vignette, to take a little bit of time with that, as well as we can do a review session as well with maybe some unanswered questions, okay? And so that's where we can approach that. I really don't think one geometry question is going to make you or break you on the exam, so it's more about understanding the geometry of what's given, okay? But I can always do a review with the entire class or individuals, however you guys want to do it, so we'll keep in touch on that. So this is a one-to-one relationship. So whatever the horizontal is, the vertical has to be exactly the same, or vice versa, okay? Because it's a one-to-one relationship. So if we have 27 kips going down, and if this is pointing down, we can see that this vector has to be pointing down towards the joint. So that means the horizontal component has to be going to the left and not to the right. Okay, so once you identify one direction on the diagonal, you can see which way the other one has to be going as well, so that it's either pushing or pulling on the joint. So that's 27 kips. Okay, we've done the sum of the verticals equal to 0, so we can check that off. What about the sum of the horizontals equal to 0? Well, now we've got 27 kips to the left, so we need 27 kips to the right. And the horizontal member, member AB, can give us that. Okay, now let's look and see what these arrows are doing. The bottom chord, it's pulling on the joint, so it's tension. If it's pulling on the joint, it's tension. And if it's pushing on the joint, it's in compression. So that has to be in compression. So what is the force in member AM? Well, the force in member AM, it's just the Pythagorean theorem. It's equal to 27 squared plus 27 squared, and the square root of that. And I believe we come up with about 38.2 kips. Okay, so we'll write in here that this is 38.2 kips of compression. And really, if you go back, you can see now that the answer has to be A. We've got 38 kips of compression. That's all we really needed to solve for, was that first joint, because that's the only one that's true. Okay, so can you see this on the exam that if that's the only correct answer for AM, you're done with the problem now? Okay. Okay, so let's move on to the next joint. Okay, we've solved this one. Now we have two choices with the method of joints. we can either go to joint M or to joint B. We have to go to a neighboring joint from which we just solved. So let's go up here to M and see what we can do. So at M, we've got a lot of stuff at M, okay? So with the method of joints, you want to put on there forces that you already determined and any loads on the member and any support reactions. Well, we already determined the force in AM and its components. They can't change from one end to the other. They have to be the same. The force doesn't change within the member. So we know that AM is in compression. So all we're going to do is draw these equal and opposite on the other side, because pushing on the joint represents compression. And so now let's put our components on there. This would be 27 kips up, and this would be 27 kips to the right. So it's equal and opposite to the other end, and it's still signifying compression. Okay, so it's pushing on the joint. Don't look at these members as a whole, because those members look like it represents tension, right? They look like they're pulling away from each other. So that's why always remember it's called the method of joints. What is the force doing to the joint? Okay, so what do we know? If we have 27 kips up, we need 27 kips down. Well, the vertical member can help resist that, and so can the diagonal. So we just can't split up that. We don't know in what proportion can we split that up. That's where that term comes from with indeterminate structures. We have too many unknowns for the number of equations. We don't know what percentage goes to each member. So let's try the horizontal. We have 27 kips to the right. Well, the diagonal member can resist horizontal forces, and so can the horizontal member. So again, we cannot solve joint M at this point. We have too many unknowns for the number of equations. So what we do then, if you get stumped on this in your other example problems that you're working, is backtrack and let's go to joint B instead and see if that can tell us anything. So let's draw joint B. And here's what we know about joint B. There's a 6-kip point load on it. And we know that member AB is 27 kips of tension. So at joint B, we have to draw this arrow so that it represents tension. So it's pulling on the joint, and it's 27 kips. Now let's see if we can solve this. We have 6 kips down, so sum of the verticals equal to 0. So we need 6 kips up. Well, member MB can give us that. That's the only vertical member that can resist vertical forces. So this has to be 6 kips, and it's in tension. And we have 27 kips to the left, so we need 27 kips to the right. And member BC is 27 kips of tension. It's pulling on the joint. Okay, so this is now determined at joint B. Now that we know the vertical, member MB, now we can put that in as one of the unknowns up here at the top. So let's put this in blue. If that's 6 kips of tension, this is going to be 6 kips of tension. Okay, now let's see what we can do with this. Let's solve for the verticals. Sum of the verticals equal to 0. We have 27 kips up, and we have 6 kips down. So we need an additional, what do we need? 21 kips going down. And the diagonal can give us that. So this diagonal has to be 21 kips going down. And it's pulling on the joint. And now you can see it's in tension because it's pulling on the joint, and that's what you're going to see with the Pratt truss. Okay? Does that answer your question from earlier, Layden, where it says how can you tell if the how diagonals are in compression or we're working it with this. So these arrows, when you put numbers into it, starts to tell you that. Okay. Okay, so now if we know, okay, so at AM, the arrow at AM, yeah, are you talking about this one right here? The first one? Okay, so the very first thing that we did was if we had 27 kips up, that was our reaction, we needed 27 kips down. And that's what tells us that it's facing down right there. The verticals are in equilibrium, so this resultant has to be pushing down. Okay, that is if we have, okay, so it looks like you got it. Okay, great. Okay, so now, once we have one component, back to, remember, MC, once we have one component of the diagonal, remember, you get the other one for free. So this has to be 21 kips to the right. They have to be equal to each other. It's a one-to-one relationship for all of these diagonals. Now we can do sum of the horizontals equal to 0. We have 27 kips to the right from the diagonal AM, and we have 21 kips to the right. So we have 48 kips to the right, so we need 48 kips back to the left. And that's what member MN will give us. So this has to be 48 kips. And that's compression. And this member is tension. Okay. Let's do one more. Let's go down to joint C, and then we'll work with our vertical force members. Okay, so now if we come down here to joint C, we have the 6-kip point load hanging off of this. And what all do we know about joint C? Well, we know that member BC is 27 kips of tension, so we fill that in. That doesn't change. So everything in blue is what we've gotten from another part of the problem. The diagonal, it's in tension, so we have to draw this arrow so that it represents tension. So that means the components are going up and to the left, and there's both 21 kips. So just taking it from what we found at joint M and putting it down here. Okay, so let's look at the vertical forces. If we have 6 kips down and 21 kips up, did I do this right? I think I did. That means we need an additional, oh yeah, it's getting less, that's right. 21 minus 6 here. 15 kips, so we need an additional 15 kips going down. So this becomes 15 kips. And it's in compression. Okay. Sorry, I stumped myself for a second there. And then if we have 21 kips to the left and 27 kips to the left, we need 48 kips back to the right. And that's in tension. Okay? At joint C. So that's what we have on this, and then you would continue to go up to the joint up here next. Okay, so this is more just practice with this, and what I want to show you on one of the last pages of the truss handouts before we talk about the zero force members is here's the truss problem worked out, okay? And it gives you the process of going through the joints. okay, to go from A to B to M to O and to so on as you go across. Also, what I want you to see here is, remember how we talked about economizing the design? And we talked about the web members carry the shear. And where is the shear the greatest? It's going to be near the supports. Okay, so look at these forces, 38 kips, 29 kips, 21 kips. They're getting smaller and smaller as you go to the inside, right? Because think about your shear diagram. It gets smaller and smaller as you move towards the middle. So you can see those diagonals and verticals, the forces are getting less and less as the shear becomes less and less in the members. Versus the chord members that resist the bending, that's at the middle. Okay, so look at these values, 38, 48, 63, 72, 75. It's getting bigger and bigger as you go across. So there's more force in the top and bottom chords due to the bending. Okay, that's what I want to show you with this. So work out half the truss, see if you can get the same answers, and if you want to keep going, it should be symmetrical about this point to make sure you've got a handle on it. Okay? Okay, the next thing that we want to talk about are the zero force members. The approach that you want to use with zero force members is sort of an all or nothing approach as a test. Okay, so let's look at our truss, and I'll give you several examples for zero force members as well, besides this one in the problem. In this problem statement, it talks about member FQ, and let's say that all they want to know is the force in member FQ and none of the other ones. And so if we did the method of joints, it would take us multiple iterations to get there. We would have to do the method A, joint A, B, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 iterations to get here. Okay, if we did the method of joints. So that's why we want to use some other reasoning and with this in the method of sections to say, can we get to the answer much more quickly? And so with joint F, let's see what we have there. And we want to know if it's, let's see, where did I put that? Okay. Let's draw a free body diagram of joint F and see if we can figure this out without doing all those method of joints. Okay, and there's at joint F, we have a 6-kip point load hanging off the bottom of this. So if we did sum of the verticals equal to 0, we have 6 kips going down and we need 6 kips going up. Well, the diagonals can both take vertical forces, and so can the vertical member. And so what we're trying to find out is what part of that goes into the vertical member. We have too many unknowns for the number of equations. So to determine if it's a zero force member, if the force is truly 0, then that means it can't even take 1 kip. It can't even take 2 kips. So that means it couldn't even take 6 kips. And I'll show you what the test is. So let's assume that all of the force goes into that vertical member that we're testing to see if it can take any force at all. So if we have 6 kips down, let's assume that this member gives us 6 kips going up. And let's assume that all of the force goes into the vertical member. The test is, can we do anything with it at the other end? And here is joint Q. So if we're going to assume that there's 6 kips of force in member FQ and it's in tension, then this member here has to be 6 kips of tension as well. Right? We put it up here equal and opposite. So if we have 6 kips down, we need 6 kips going up. Well, a horizontal member cannot resist a vertical force. So no matter what vertical force you put in this member, it can't take it at the other end. It has to be 0. Okay, because even if we said 1 kip went in there, it still would be no good at the other end. So all of this force has to go into the diagonals. Okay, so that's how we can determine very quickly if FQ is a 0 force member. Can you do anything with it at the other end? A common one that's very similar to this is the king post truss. And I think in your take-home problems, I've got this in there as well. In one instance, let's say we put 1 kip on the top. And in another instance, let's say we put 1 kip on the bottom. So in truss A, and this can be truss B, if we have 1 kip going down, we need 1 kip going up. Does it go in the diagonals or does it go in the vertical? Well, if we put it in the vertical, we show 1 kip up and then it flips at the other end. It can't go anywhere. So loading a king post truss at the top, this has to be 0. All the load goes like this down the sides. And the middle member does not take any load. And I'm being very careful with choosing my words with that. It doesn't take any load, but it doesn't mean you can remove the member. Okay, I get that question all the time in class that says, hey, can you remove the member from there if it's a 0 force member? And I would say no, they do other stability things like bracing the compression flanges and things like that. Okay, so in one instance it doesn't take load, but in other conditions where the load is not uniform or we have patterns of loads, it may take a load, and also these members provide bracing points for the other members. So I would say, if you're asked a question in your study guides and so on that say, which member can you remove from the truss? What they're really asking is, which member is a 0 force member? They're not asking you, okay, so engineers aren't going to remove members from trusses just because. If it doesn't need to be there, we won't put it there. But, okay, so just to let you know, the wording of that question, sometimes it throws people off when they say, which member can you remove? Well, they really don't mean can you remove it. They're really asking, is it a 0 force member? Okay, so what if we put the force on the bottom? Well, if we have 1 kip going down, we need 1 kip going up. The horizontal members can't resist any of that force, so it has to go into the diagonal. So now in this instance, this diagonal is a 1 kip member. So it goes up, it pulls on the top, and then it goes down the sides in compression. So there's where, in our previous example, if the 6 kips was at the top instead of the bottom, then it would be 6 kips in that member, okay? Because it would need to push down all the way through the system and then inject it into the diagonals. So it matters which side you're loading it on as well. Does that make sense to everybody? The litmus test to see if it's a 0 force member? Okay, good. And that'll help you save some time. We'll talk about the method of sections, and then I'll show you the last page in this. So the method of sections, we're just going to do one example with this, and I'll show you an easy way to visualize it as well. We'll do section cut number 2. So let's talk about the rules. Okay, so the rules with the method of sections. Well, we always start with solve the support reactions. Okay? And so either the method of joints or the method of sections, we need to do that. And this is going to be a time saver for you on the exam, okay? It's not going to be such a complex problem, I would assume, that you need to use this and have a 30-minute problem on it, okay? So we're going to use it as a time saver and just talk about the rules. So we cut a section through the truss, And the section needs to be cut through 3 members. And let's say we want to find the force in member PQ, okay? And it's way out here in the middle of the truss. And this is where it becomes a time saver. We can find that force using the method of joints, and that's what I would use. I prefer it. Okay, I'm more comfortable with it, and it's only going to take you a little bit more time to do it, but use with what you're comfortable with. If we did the method of joints again, it would take us 1, 2, 3, 4, 5, 6, 7, 8, 9 iterations before we got there. So let's see if we can do the method of sections and find that force in member PQ much more quickly. So the section should be cut through 3 members. The first member cut through should be the member under investigation, so we want to cut through PQ. The other 2 members cut through should share a common point that is not common to the member under investigation. So we're also cutting through PF and EF, and they share this common point of F out here, okay? Then we take moments about this point that is common to the 2 members and solve for the force in the member under investigation. The only forces used when taking moments about the common joint are the support reactions and the applied loads, okay? So what we're really doing is, instead of looking at an individual joint and isolating it, we said that every part of the element or truss has to be in equilibrium. We're just taking a bigger joint. We're just taking a bigger piece and finding the equilibrium. So no matter what scale you're looking at, on a very small scale or big scale, it has to be in equilibrium. The thing with the method of sections is your arrow is not going to tell you if it's in tension or compression. You have to know what you assumed, okay? And that's where this takes a little bit more visualization to do this, because even if your answer comes out positive or negative and it says flip the arrow because we're just going to take moments about a point, you have to know what your initial assumption was. So let's try to, I'm going to draw this so that we can visualize this a little bit better. So let me see how many joints there are. 1, 2, 6. Okay, so let's, I want to draw this vertically. I exaggerated the scale a little bit horizontally. Because a braced frame is just a vertical truss, okay? And I'm going to put supports down here. Okay, this is what, when we cut a section, what we're really doing is saying, if this is the point we're taking moments about, if this is point F, what we're saying is, find out what's going on above this point or below this point. So we have A, B, C, D, E, F. I guess I'm off by a point, huh? And this is M, N, O, P, and Q. Okay, so a braced frame is just a vertical truss, okay? And let's approach it like this. I think we can better visualize what's going on. And so at A, which is our support reaction, we have a 27 kip load. But at B, C, D, E, and we can also put in at F, we have these little 6 kip loads acting the opposite direction. Okay? And we want to find out what is the force in member PQ. Okay, that's what our goal is. So when I look at this, if every one of these, I believe they're 10-foot increments, we have a 27 kip load that's 50 feet off of the ground. If we're taking moments about F, and this 27 kip load is causing clockwise rotation, okay? At 27 kips times 50 feet off the ground, is that greater than all of these 6 kip loads that are at 40, 30, 20, 10, and 0 feet off the ground, causing counterclockwise rotation? I'm going to assume that they are. I think the net overturning is going to be in the clockwise direction, because that 27 kip load put way up high seems like it's going to tip this thing over to the right more than those little 6 kip loads going back. Do you guys agree with that? Okay, so here is where we have to make that initial assumption. What are we assuming and why I tipped it up so we can visualize this? If we have 27 kips tipping over times 50 feet off the ground, it's pushing this side of the frame down and pulling this side of the frame up. So I'm going to say as it pushes it down to the ground, that this has to go up. This side is in compression. So my initial assumption now just isn't an arrow direction of going up. It's saying that if the ground is pushing back, then PQ is going to be in compression. Okay? That's why you have to understand if you're looking at tension or compression. Okay, so what we do then is let's take moments about F. So sum of the moments about F. Well, that's equal to this 27 kip load times 50 feet off the ground, and that's positive. It's clockwise rotation, minus 6 kips at 40 feet, minus 6 kips at 30 feet, minus 6 kips at 20 feet, minus 6 kips at 10 feet. We could include 6 kips at 0 feet, so we might as well. Minus 6 kips at 0 feet. Okay, those are all the loads. And what we're trying to find is this reaction. And my assumption is that it's going upward. Okay? And so that is going to cause counterclockwise rotation about F. And it's at a distance of 10 feet away. Okay? So it's that perpendicular distance. So it's going to be minus our reaction at PQ at 10 feet away and set that equal to 0. And what we're going to end up with is, I believe, 750 kip feet. Let me make sure. Yeah, 750 kip feet equals 10 P sub Q. Okay, and what we see then, if divide each side by 10 feet, and we get P sub Q, or the reaction of P sub Q is equal to 75 kips. Our answer is positive, so that means we assume the correct direction. So what did we assume? We assume compression. That's where you have to know in the method of sections, what is your assumption? Is it tension or compression? And so that's why I did a little bit of, let's turn it up on its side. I myself can visualize things a little bit better like this, and it still works the same. And maybe this gives you another toolbox to do that. You can see that going through all this is really not going to save you much time doing the method of joints by putting together all this equation, okay? But the answer comes out to be 75 kips of compression. And if we look back at our picture, now we can see if we push up with the, let me go, okay, if we push up, I'm on the wrong page in my book. I need to go to page 252. Okay. So if we push up on this, it's going to try to bend this truss in these directions. And about this halfway point of the truss, this thing is doing the same thing. And so that's where it starts to bend this top chord in compression, okay? So each side, about that half, is being pushed upward. So if you can visualize the top chord being in compression that way, you'll get the same answer. Okay, so it's just visualizing and understanding, do you think it's going to be in tension or compression, and understanding that assumption. Okay, so that's the method of sections. And let's talk about the last zero force member. Remember this truss? We found the reactions on this truss when we were looking at support reactions. And here was that 2 kip horizontal force. Okay, and we said that all of the 2 kips had to go to A because J is on a roller and cannot resist any horizontal force. So what happens, I would say, this gives you an additional problem to work with all the answers right here, and we can see that HJ comes out to be a zero force member. Well, let's say that this was 1 kip as you're going through because you have a mathematical mistake and you've got an extra 1 that you start carrying through this, okay? So let's say that on H you've got 1 kip of tension, and then you're to this final joint. And at the final joint, you've got your roller, your reaction of 22.25 kips, and carried over from this other joint, we have 1 kip of tension. Okay, so if we have 22.25 going up, we need 22.25 going down. And that works for the verticals. But what about the horizontals? If we have 1 kip to the left, we need 1 kip to the right. Well, we don't have a diagonal or horizontal member here to resist it, and our support reaction cannot resist any forces either. So this has to be a zero force member because, again, you can't do anything with the horizontal force at this end. So that's showing you at the support reaction, if it's a roller support, that you've got a mistake, probably an addition or subtraction mistake somewhere back here that this 1 kip is carrying through, okay? So go back and look at that because this has to be 0 at this location based on the rules of that pin.